2.6, this is our last discussion on looking at limits before we are able to talk about the derivative, which will come in 2.7. 2.6, limits at infinity. Once we discuss this, we'll know all we need to know about limits for the time being before moving forward. Really exciting. Okay, what are limits at infinity? We did infinite limits before. These are infinity is in a different position for these. Okay, so you may recall end behavior, that concept from pre-calc. End behavior, what happens as x approaches infinity and as x approaches negative infinity? It's like what's happening on the ends of the graph. What y value is the function moving towards as you get way out on the x-axis in either direction? So we've kind of got this limit notation, right? X approaching infinity or negative infinity already going on. Let me provide an example here, and we can do one where we can see a graph. So here's the graph of 1 over x. This is going to be a good starting point. So 1 over x, of course, it has that vertical asymptote there at 0, but it also has a horizontal asymptote as the x-axis. Okay, so what if we were to think about these limits here? And I think they're both going to kind of be a side-by-side on the screen. Hopefully I can get this all to fit. The limit as x approaches infinity, positive infinity, for this graph 1 over x. So we're thinking, okay, we're out here and the x values are increasing and they're just going up and up and up. X is approaching infinity. Of course, it'll never get there. It's just going to move on forever. What is the y value approaching as x gets bigger and bigger and bigger? Well, I already have it written there, but of course that y value is getting smaller. It's tending towards 0. It will never actually reach it, but it is approaching 0. So there's the answer to our limit, as the limit of 1 over x as x approaches infinity is equal to 0. What's happening back here on the other side, the other end behavior? As x approaches negative infinity, what's the y value approaching here? Well, it's still headed towards 0 just from the bottom side of the x-axis, so that is going to equal 0 as well. When it comes to dealing with infinity this way, and in these, and maybe more so in the problems, the examples we're going to see in a few minutes, wrestling with the idea of infinity tends to give the human brain a very difficult time. We're used to working with finite numbers that we can wrap our head around, that we can imagine, and infinity just doesn't, it goes beyond that, right? So even though probably this one people can see it and they're okay, I'm also going to approach this with a table. So we've got the graph. Let's look at the table version as well. Now we're not going to approach examples later on with tables and graphs, but I think it's helpful here just to get an understanding of maybe algebraically why these are headed towards 0. That will help us out for the later examples too. So here's what I've got. Kind of go about this far. I think I'll cover up my note for the moment. Okay, so we saw this graphically. What if we were to approach it with the table? 1 over x as x approaches infinity. So I'm going to take some values of x that are getting bigger quickly. So 10, 100, 1000. Let's see the behavior as it moves. Well, if x is 10, then of course 1 over x is 1 over 10, but maybe I'll even write it as a decimal, right? That's 0.1. What if x is 100? Well, 1 over 100, 0.01. And finally 1000, 0.001. Like, okay, maybe that's helpful. As x is getting bigger and bigger, that decimal is getting smaller and smaller. It's always positive, but it's definitely headed towards 0. The bigger this number, the closer this is to 0. How about the negative case? As x approaches negative infinity. Well, let's take negative 10, negative 100, negative 1000. Well, let's see. Wouldn't this be negative 0.1, negative 0.01, and negative 0.001? It's on the negative side, but you know the distance from 0 is shrinking, right? It is headed towards 0 that way as well. Okay. Before moving on to more difficult examples, just want to make a quick observation here. Note, limits at infinity are always one-sided limits. Okay, so we don't write the little negative or the plus because they would have to be, but as x approaches infinity, right, you can only do that from the left side. Right? You can't approach infinity from the right side. You can't go past infinity and come back, right? So, okay, so that's always from the left, even though we don't write it. And as we approach negative infinity, you can only approach negative infinity from the right side, headed back that direction. Okay, so for what that's worth. All right. Moving on to more difficult. Now that wire kind of hanging down in my way. Moving on to more difficult problems. This section, it's just going to be a ton of examples. There's no more theory per se beyond what we've discussed already. We just got a whole bunch of examples we're going to slowly work through. See different circumstances. Okay, find the limit. This one looks a bit like what we just saw there with 1 over x. The limit as x approaches infinity for the function 3 plus 2 over x minus 1 over 5x squared. Okay. So we can kind of see this dividing by x, dividing by x squared here. Let's think about this. So one attribute of limits, which I think will be helpful to highlight here, if you're ever adding or subtracting terms, you can take the limit of each one separately. So I've got that as my first step. We haven't done this before. It really hasn't been necessary or enlightening to any of the problems that we've done to do this. It would have just been like these extra tedious steps. But I think it's helpful here, and hopefully you agree, that if I'm taking the limit of, these three terms being added and subtracted, I could take the limit of each one separately and then put them all together after the fact. Okay. Well, let's see. If I take the limit of 3, as x approaches infinity, what happens here? Well, imagine that graph, just the 3. That's a horizontal line, right, at 3? Well, as x goes off to infinity, doesn't y just remain at 3, the horizontal line? Okay, so if you ever taken the limit of a constant, the answer is just the constant, because think of the horizontal line as x goes to infinity. Actually, it'd be true for no matter what x was approaching. If it's a constant, that's just what the y value is. Okay, so that's kind of interesting in its own right. But now let's move on to here. As x approaches infinity, what's happening with 2 over x? Well, in the same way as 1 over x went to 0, same thing's going to happen with 2 over x. It happens to be twice as big, but that denominator is getting bigger and bigger and bigger, which is going to make this whole thing get very, very small. It's headed towards 0. And then finally, this last one, well, now we've got a square. So as x is getting larger, this denominator is getting really big, really fast with the square. So 1 over 5x squared, with our denominator getting very, very big, that's headed towards 0 as well. So we can come to this line. We had the 3, both of these headed towards 0. And so we can see our answer there is simply the 3. And we got it. If you're having trouble with maybe, any one of these, but especially maybe these second two, create a quick table for yourself, or even look at the graph of these individually and convince yourself that these are really going to zero and why that's true. I think tables are a lot of times helpful here. Okay, let's do something a little bit harder. No more polynomials, although some of the concept is going to carry over. Let's look at the limit as x approaches infinity for 4e to the negative x. Like, oh, wow, okay. E raised to the negative x. I'm going to begin by rewriting this. Isn't e to the negative x? Can't I put that e to the x in the denominator and it will become a positive exponent? Like this? It will be easier to think about this way. Why is that? So let's think here. So if x is getting bigger and bigger and bigger, what's happening with the denominator e to the x? And well, I'm kind of showing all of my work here. As x goes to infinity, as x gets bigger, isn't e to the x going to infinity as well? Actually, way faster, right? So as that exponent gets bigger, then that number just gets larger and larger and larger. That means we're dividing by infinity, if you will. We're dividing by a really big number down here. The numerator is just staying at 4. So 4 being divided by bigger and bigger denominators, the whole thing's getting smaller. It's going to 0, just like back in these cases where those went to 0. This one is as well. Again, if that's not quite clear to you, hey, we're talking about infinity here. This baffled very, very intelligent people, some of the smartest people in the world developing mathematics. It baffled them for thousands of years. I mean, we're even going back to Plato and Socrates and those guys. So if you're like, well, why is that happening? Maybe convince yourself by making a table or maybe a graph. Okay, I got one more for this video. It's similar to part B. Let's take this limit to negative infinity. Still 4e to the negative x. Okay, this is interesting. Actually, in this one, I'm not going to rewrite it as the fraction. Why is that? Think of plugging in, if you will, the negative infinity. Okay? If we put in big negative numbers in for x, wouldn't that cancel out with this other negative? Well, it looks like I'm showing you all of my work here. So as x approaches negative infinity, that negative infinity goes in there and the negatives cancel and it's back to just e to the infinity, or e raised to really large numbers. That's going to infinity now. And well, 4 times infinity is just a bigger version of infinity. And so there's our answer to part C. Again, if this is not quite clear why that would be going to positive infinity, make a quick table, maybe use x equals -10, -100, -1000, plugging those in. And I think you can convince yourself that this is what's happening very quickly that way. Okay, let's stop this video here. We got lots more examples to come.